Hi, my name is Aditya and I am the CEO of Automaski. Today we are going to be talking about quantum annealers and I'm going to give you four more reasons why quantum annealers are crapware. So let's get started. But before that, we want to mention a couple of things about Automaski. We've been working on complexity theory since 1980s, late 1980s. We solved P is equal to NP in early 1990s. We got into quantum physics in mid 90s and within a few years realize this universe is a simulation and that too a linear order simulation, and that implementing physics won't require of the order of 2 to the power 3 n complexity but rather order n complexity. We developed our rudimentary quantum computer a few years later, but only in 2014 when there were massive publications we figured out which gates to implement and what algorithms to benchmark and test with, hence implicitly achieved quantum supremacy in early 2015. 2 years back we simulated quantum gravity with a billion qubits. And 6 months back, we publicly launched our RSA 2048 cracking service available for anyone who cares to pay money and use it. Till then, it was available only to Department of Defenses and agencies around the world behind closed doors. And today, we are working on our quantum gravity computer based on causaloid formalism. Again, the core quantum gravity computer has been ready for years now. We have been playing with it and trying incremental changes, just that we don't know how to make use of it because there is nothing published or available out there which shows how something like a quantum gravity computer can be used to solve real world problems. A small piece of advisory, please proceed with caution. If this presentation goes against your belief system, then please ignore this presentation, stop the video, and focus on things you are passionate about. If you are respectful and polite, I would love to answer any questions you might have or listen to your thoughts. Feel free to email info@automaski.com. Now let's establish a common baseline understanding before we get into the arguments. Otherwise, you will not understand the argument itself. There are many kinds of problems you want to solve on a quantum annealer. Traveling salesman problem is one of those problems. Now, what is this problem? This problem basically states that if you are given n cities and the distances between those cities, the problem is to start from any one given city, visit all the cities exactly once, and come back to the starting city in the shortest distance possible. This is also called as route optimization. It is used by logistics companies, delivery companies, taxi services, airlines, factories, warehouse planning, robots, autonomous cars, drones, etc. etc. So, obviously, it is a very important problem, but it is NP hard to solve. For the purposes of our discussion, let's agree on two things. We will call the number of cities in this problem as the number of variables. Cities is equal to variables. This is the original traveling salesman problem definition. Okay. And the number of qubits we need on a quantum annealer to actually solve this problem, we will call it the number of qubits. So let there be no confusion between the number of variables and what the number of variables means and the number of qubits, what it means. Now, the first reason why quantum annealers are crapware. If you have a traveling salesman problem with 50, 100, 150 or 200 qubits, just look at the graph above. There are ways of encoding it into a cubo problem. Okay, and a cubo model is basically something that the quantum annealers can solve. So, for every variable, for a problem of given number of variables, you typically require of the order of n cube, uh, you know, uh, qubits in the cubo formulation. Now, as shown in the graph, for n is equal to approximately 250 cities, we need a cubo model with about 10 to the power 7 raw qubits. That's 10 million raw qubits. Okay, but that is not all of the problem. Let's look at the second reason. Now, as you can see from documentation above, there is something which needs to be done, which is called minor embedding. Quantum annealers have very limited connectivity in their underlying architectures between the qubits, and they cannot execute arbitrary cubo models. So we have to transform a cubo model into a different graph or a different cubo model which accommodates the connectivity limitations. And this requires n square the number of qubits of the original qubits. So if you have a TSP problem with some variables and you get a cubo problem of k qubits, you will now after minor embedding require up to k square qubits on the quantum annealer. Now if you combine the first and the second reason, we arrive at the conclusion that for a TSP problem with approximately 250 variables, we need 10 to the power 7 raw qubits cubo problem, but after minor embedding, we need to square it, and we require 10 to the power 14 qubits on the quantum annealer. If you don't understand how big that number is, then it is 100 trillion qubits, all for a TSP problem of just 250 cities. The third and the fourth reasons. Even after doing all this, the solution that quantum annealers give have broken chains, also called as broken constraints. And the optimization results are grossly suboptimal, the quality of solution vis-a-vis the theoretically best possible solution. Classical heuristic solvers routinely solve TSP problems with tens of thousands of cities and variables. We can extend the entire argument in this presentation to all other problems we want to solve on quantum annealers without any loss of generality of the arguments and the conclusions. One can argue, though, that sometimes we don't need the best solution but rather a quick and dirty solution. You be the judge of that. This is precisely the reason Automatsky released and offered its quintillion annealer. A quintillion means 10 to the power 18. And that is the number of qubits the quintillion annealer from Automatsky supports. And since Automatsky's quintillion annealer does not have connectivity issues and doesn't require minor embeddings, we will be able to run production grade problems of about 1 million variables. So a traveling salesman problem with 1 million cities is something we can solve on the quintillion annealer. Because 1 million cube is 1 quintillion. So, that way. You might not want to believe it, but either way, this is the way it is, and it is not going to change. Congratulations and enjoy. You take the blue pill, the story ends. You wake up in your bed and believe whatever you want to believe. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes. Remember, all I'm offering is the truth, nothing more. Thank you, and hope you have a nice day.